And good afternoon, everybody. So let's take a look at some topics for the review today. And we're going to take a look at some questions, or rather concepts, as well as questions that could be encountered on the final exam. Of course, we physically cannot embrace everything that was studied throughout the semester in the past at this point, but we'll take a look at some kind of like fundamental things and then try to branch off from them. So to begin with, so let's just again think about some items, right? So like what we need to keep in mind is going to be item number one, so which we can put under the umbrella of hybridization and geometry, right? So when we talk about the geometry, we can encounter something like that. So this is the representation of the tetrahedral geometry alongside the sp3 hybridization, right? Or vice versa, sp3 hybridization for the carbons, right? Of course, we're talking about the hybridization of the carbon atom in this organic chemistry course. So if we think about the carbon with 4 single bonds that are attached to that, and then someone else can be attached to those bonds in turn, maybe as simple as just 4 hydrogens, right? Total. Then nevertheless, we're going to be kind of thinking, okay, well, this carbon, it has the sp3 hybridization, and the geometry will be tetrahedral, as shown in this schematic. So next we move on to the so-called unsaturated compounds, right? So that's another term that you have encountered a lot. That's when we talk about some sort of carbon-containing compounds which feature a carbon with a double bond, right? So now the carbon still remains tetravalent, but it has 1 double bond and 2 single bonds, right? Or 4 bonds total. And then it can have some sort of attachment, right? Maybe a couple H's here, maybe here's going to be another carbon that is also that also happens to be kind of like in this particular hybridization state, right? And then we have some kind of like substituents like more attached to that carbon, right? So in this case, this carbon or that carbon are in the state of sp2 hybridization, and then they have the trigonal planar geometry. Last but not least, we have also seen the carbon that features the combination of 1 single and 1 triple bond, total 4 bonds as well. So because carbons are tetravalent, they are not like di or pentavalent, right? They are tetravalent, but we can have different combinations of the bonds surrounding the carbon in question, right? When we look at this one, so we will know that it is sp hybridized, and then the geometry here will be linear because it literally looks like a straight line, right? So yeah, this is just something to keep in mind in terms of the hybridization and geometry. So then from there, we can move on to a little bit of the macro properties of the compounds, right? So like what we were looking a lot at, which was kind of a common topic if you think about that. So if you move, for example, from, let's say, alcohols towards carboxylic acids, right? So there's going to be something in common that those compounds share. And then this is hydrogen bonding, right? So that was one of the like very common intermolecular forces that exists between molecules of either the like same compound, if possible, or different compounds, right? So for hydrogen bonding, so like HB, let's call it HB. So we need to have something, right? Such as prerequisites. For example, it's going to be the existence of the specific bonds, such as OH. Maybe it's going to be FH, right? Or some kind of like halogen with the hydrogen, basically, right? So, and also what else? NH, right? So these are kind of like 3 types of bonds. Of course, there are going to be like more halogens, right? So then just fluorine. So make conclusions to yourself how many total bonds there will be. So, but that's what we need to have, right? So like these bonds, they will be highly polar because of the like substantial difference in electronegativities between the oxygen atom and hydrogen. And same can be true, same is true about fluorine H and nitrogen H combinations, right? So then here you can recall kind of like the general term electronegativity, right? And then if you are still kind of like in the dark, which hopefully you are not by the end of this intense semester, you should be able to kind of like define what electronegativity is, right? And how it can be exemplified between atoms of two elements at the very least, right? So, well, typically two atoms of the elements, same or different, right? So that's where we need to be concerned with electronegativity, for example, right? So if the difference in electronegativity is pretty high, right, then it could lead us to the hydrogen bonding. So, and then it could happen between compounds which feature these bond types, right? So then what happens, right? So when you look at hydrogen bonding, you can show it generally, right? So maybe let's just take a look at the deep end, which is going to be the carboxylic acids, right? So because coincidentally, we will have the OH bond, good, right? So now we have like one of the prerequisites kind of like checked for the hydrogen bonding. And of course, we need to have like other molecules that will be able to combine with just like some sort of molecule of interest, right, via hydrogen bonding. Okay, so if we look at the carboxylic acids, they can do the hydrogen bonding in particular. So if you look at if you look at this topic a little bit further, so they form the so-called dimers, right? So this is what is peculiar about carboxylic acids. And then we can show them as such, right? So why do we show them as such? Because we are kind of here concerned about the distribution of the charges, right? So what do I mean by that? So due to the electronegativity of the elements, especially substantial difference between the electronegativity of certain elements, we are going to form on them the so-called partial positive, partial negative charges, right? So the atom, which is less electronegative, will be having tendency to kind of like lose electrons, right? Partially, right? So that's why we're going to generate, like before the like breakage of the bond, that can happen under other circumstances. But before the breakage of the bond is still there, right? But it's polarized. So because this kind of like electron density, which is represented by those two big dots, is shifted to like one atom rather than the other. Okay, I need to find my charger just a second. So, and then in this case, you are going to like understand, okay, well, since oxygen is more electronegative, it will be drawing the electrons towards itself, right? Because according to the kind of high school definition of electronegativity, that's what electronegativity is about, right? So it's about the ability of the atom to pull electrons towards itself. And then consequently, so like from the neutral, right, by default oxygen atom, we are going to move to a delta minus, right, partially negative charge, because it gets maybe, let's say 0.25 of this electron from hydrogen, right? And it becomes partially negative, right? Doesn't get the entire -1 charge, it gets 0.25 of the negative charge from the electron belonging to hydrogen originally, right? So that's why we're going to say, okay, well, it's going to be like minus 0.25 charge, right? So partial charge, not full -1 charge. That's why we have this delta minus, right? So delta stands for the partial kind of like partial charge, right? So, and then it's negative because it gets a little bit of this electron from the hydrogen. Hydrogen, being the one who is losing a little bit of the negative charge, will become partially positive, right? So that's just a by exclusion, right? That's what you can think about. So if something kind of like loses an electron, right, it becomes positive, right? So that's when you talk about the loss of the like complete loss of the electron. So by extension, if you have like partial loss of the electron, then you will have a partial positive charge being developed to counterbalance this partial loss of the negative charge, right? So then by the same token, so we'll have the delta minus, delta plus, right? So then here we have delta plus, delta minus, and delta plus and delta minus. So then from physics, we know that the opposite charges will attract, and then this will kind of like give us the way towards the hydrogen bonding, which is typically marked with the dotted lines. All right, so here we go. That's a hydrogen bonding between the like two molecules of the carboxylic acid in this case, right? So if you have some other molecules, right? So such as maybe like COH, right? That can be a little bit trickier, right? So here you have COH, so it's going to be some sort of aldehyde. And then R will be, for example, butyl, let's say, right? So you need to know what butyl is at this point. I will not even show it, right? So that's for your review purposes, so to speak, right? What's butyl? Well, go ahead and then draw that for your like practice purposes, right? So if we look at the molecule of this like pentanal in this case, right? So we have butyl here, let's imagine, that's our group, and then carbon, 5 carbons total, right? So in addition to the 4 carbons of the butyl, then we are going to have pentanal and aldehyde, right? So aldehyde has this like CH bond, then it has like this non-polar butyl group, right? About which we don't care when we think about the hydrogen bonding, and it has a CO bond, right? But those bonds that don't fall under the hydrogen bonding realm, so consequently, we cannot kind of make the hydrogen bonds between the individual molecules of, let's say, aldehyde, right? So, but if we, let's say, throw in some water molecule next to the aldehyde, right? So I'm going to do like that. So then we are going to have here delta minus, delta plus, and then we're going to have the OH bond, which is good for hydrogen bonding, right? So that's going to be our hydrogen bonding agent. So, and then it can make the bonds, right? So between the water and the what's it called? The aldehyde molecule, because in the aldehyde molecule, even though we don't have the hydrogen bonding eligible bonds, right, it has still the partial positive and partial negative charges, right? Just like this. So, and now if we look at the situation, so like if we kind of like look at this like hydrogen molecule, hydrogen atoms in the water, then we will see that we are going to have the attraction between the partial charges between, let's say, aldehyde molecules and the water molecules, right? So this way, we will be able to form the bonding between the two molecules, right? So, because one of them provides the hydrogen bonds necessary for the hydrogen bonding formation, right? And the other charge, the other molecule provides the partial positive, partial negative charges. And then they will be able to interact and then participate in this kind of like hybrid hydrogen bonding between the molecule of water and the aldehyde molecule, right? So, but the aldehyde molecule by itself cannot make hydrogen bonds, right? So, however, it can participate in this kind of like dipole-dipole interaction, because if you think about it, you'll have the dipole moment here, right? So that's kind of like shown like this, right? And then if you put another, let's say, aldehyde molecule next to this aldehyde, then you'll be able to have some kind of like dipole-dipole interaction, right? Let's say, so we have delta minus here and H, right? And then you can have this delta minus interacting with the delta plus, but it's going to be not a hydrogen bonding because you don't have bonds eligible for the hydrogen bonding present in the aldehyde molecules, right? But they will be able to have the dipole-dipole interaction. So that's kind of the distinction, right? And then if you, again, add the water molecule into the mix, then you will have the kind of like at least partial hydrogen bonding, because you have one molecule at least with the bonds eligible for hydrogen bond formation, right? So here you go. That's your kind of like things, right? So then related to like intermolecular interactions, which will give an impact towards the boiling points, right? So we were thinking about how kind of like the boiling points of alkanes, for example, are low, right? So because if you look at the molecules of alkanes, they will only have dispersion forces, right? So dispersion forces are pretty weak, and then they will be able to give rise to the fact that alkanes boil at very low temperatures, right? So sometimes it's even negative temperature, like negative 16 Celsius, and then it already kind of like goes from the liquid alkane to the like vapors, right? So and at like a minus 10 Celsius, let's imagine some kind of like alkane, relatively short chain, will be already like a gas, right? So pretty crazy to imagine that, but this happens a lot because, so we can explain it. So because here we have the dispersion forces, right? So that take place between molecules of alkanes. They're very weak, so consequently you need to apply just a little bit of heat to disrupt those forces and make the molecules far away from one another, thereby creating the gas phase, right? So if you have some sort of alcohol, then in that case, you will be already in a different situation. Let's imagine we have 1, 2, 3, 4. We have one butanol, right? And then this one butanol molecule interacts with another molecule of one butanol as such, right? So here we have OH, and that's going to be 1, 2, 3, 4. So they will have the hydrogen bond in between one another. Why is that so? Because they both possess the OH bond, right? So, and then you will have your delta minus, delta plus situations in both cases. So then you'll be able to be like, okay, well, let's kind of like put them together and see what happens. Delta minus interacts with delta plus, and then you have the hydrogen bond formed, right? So hydrogen bonds in the hierarchy of strength are stronger than dispersion forces bonds, and then consequently it's going to take more energy in terms of the heat, right? So to evaporate the molecules of alcohol, right? So it will take more energy to disrupt the hydrogen bonding because it's stronger than the dispersion forces, and consequently you'll need to like have higher temperatures to boil the alcohol, right? And the alcohols of the comparative size, with alkenes or like alkanes, molecules will boil at much higher temperature, right? So let's say, so this alcohol will potentially boil if we give it more carbons, maybe also make it like 6 carbons, right? So that becomes 6 carbons. And 1, 2, 3, 4, 5, 6. So this will boil maybe at, let's say, 57 degrees Celsius, right? Which is substantially higher than minus 16 Celsius. So yeah, just something to keep in mind, right? Also, another element, like pun intended, that brings some impact to boiling points is the branchedness, right? So if we like look at those alkanes, both contain 4 carbons, both are alkanes, but this will have a lower boiling temperature because it's branched, right? And then if we look at the branched structures, they will have slightly larger distance between the molecules of itself, whereas the linear alkane will have the ability to kind of like closely pack, right? And then this distance is much smaller. Consequently, it will take a little bit higher force to vaporize those molecules than these molecules, since they are farther from another, so less force to evaporate them. So consequently, lower boiling point, higher boiling point. So that's just something to keep in mind, right? So then what else can we think about? Some kind of general chemical processes, right? So like consider that as a hint, right? So what we saw a lot was oxidation versus reduction, right? So that was kind of a common theme in a lot of our exams, building up to this final exam. And it's going to be kind of like a big theme in organic synthesis as well, right? So let's take a look at what's it called, reduction, right? Reduction versus oxidation. So when we think about some of those processes, right? So like it's always a good idea to show some examples, right? So because chemistry is experimental science, it deals with some kind of like properties of particular chemicals, right? So and then if you want to like show something, then it's going to be like required actually to show the schematics, right? If you think about, okay, well, what is reduction versus oxidation, right? So here you go. So you can take a look at your good old alcohol, right? So let's just start with the primary alcohol here, and then it can undergo the process of oxidation, right? So it has here at this locus a bunch of hydrogens, right? So if we want to oxidize it, so we can oxidize it in basically like a couple fashions, right? So one of them will be like mild oxidizing agent, MOA, according to our abbreviations in our presentations at least, right? So we will have mild oxidizing agent versus SOA, which is going to be a strong oxidizing agent. So this will lead us to a different result, right? So either way, we'll take a look at the oxidation processes in both cases. So what is oxidation from the organic chemistry perspective? So this is going to be, in our case, the situation in which we're going to either increase the number of oxygen atoms in the resultant molecule, or we will decrease sometimes at the same time, right? So concurrently, the number of hydrogen atoms, right? So if we apply the mild oxidizing agent to this primary alcohol, we are going to obtain the following molecule. So this molecule will be here, so it's going to be R, so this just group stays intact, right? Then we are going to make an aldehyde out of this, right? So by this. Okay, drawing. So now take a look at what happened to this kind of circle locus. So here you go. You have carbon, carbon. Okay, good. So you used to have three H's. Now it's only one, right? So technically we did have the oxidation, right, happening. So because we reduced kind of, or let's say decreased the number of H's, right? So we went from 3 to 1, and the number of oxygen stays the same, but it's okay. So we still followed one of the tenets of reduction, which was the, or oxidation rather, which was the decrease in the number of hydrogens, right? So, and then you go from alcohol to aldehydes. That's a common reaction that falls under the oxidation type, right? So strong oxidizing agent will bring you slightly different result, right? So, and it will be manifested via also the increase in the number of hydrogens, sorry, in the number of oxygens, right? So if you increase the number of oxygens in your molecule, then you are also undergoing oxidation in this molecule. So here you go. You go from the one oxygen to two oxygens. So you do have the oxidation process exemplified. And then also you go from three hydrogens to one hydrogen only, right? So you also have kind of the oxidation happening in these circumstances as well. So yeah, we here arrive at the carboxylic acid, right? So, and at the same time, you can think about some kind of like examples of chemical reactions, right? So specifically, what happens if we oxidize alcohols, right? Primary alcohols, for example. What are the pathways? Here you are. So here they are in front of you, right? So then you can think about some kind of other alcohol oxidation, right? So such as secondary alcohol. So here just kind of like give information, and then maybe you kind of like don't remember that, so then it will kind of force you to review what you don't remember, right? Or maybe you kind of, okay, well, I'm on it, so I know what happens in the oxidation cases for primary alcohols. I know what happens in the oxidation case for secondary alcohols, right? So, and I know what doesn't happen in the case of oxidation of tertiary alcohols, right? So this is going to be like another thing here with a caveat. So yeah, just like something to like think about. So because those are very common reactions, they can be encountered a lot. So it's good to keep them in mind, right? So then we're moving on to item, whatever it's going to be, potentially 4, maybe 3, who knows? So it's going to be about our acid-base reactions, right? Which again was a very common topic in organic chemistry course this semester. And then this is something that carried over from the previous chemistry, such as like general chemistry, maybe introduction to general chemistry, whatever you're taking as a prereq for this course. And this can also like show up in, let's say, your medicinal career, right? Medical future, if you will, or maybe it's going to be something related to biological career of yours, right? So depending on your major. So, but it could also be like fair game, right? So here we're going to be concerned with the acid bases, conjugate acids and conjugate bases, right? So very common terms that we come across a lot, right? So here we go. Let's take a look at that situation, right? So typically what happens is the following scheme takes place. Acid reacts with the base, and in our case, we were looking a lot at weak acids, specifically carboxylic acids, and weak bases, specifically amines, right? So that's where we were in our acid-base journey this semester. So what happens is that the parts of the journey from general chemistry show up again, right? So acids, upon interaction with the base, make the conjugate, right? So what do they make? So as we were saying, they will make the opposite of itself, right? The opposite of acid. If we like look at acids and bases, who is the opposite to who, right? So acid are opposite to base, right? Consequently, acid makes the so-called conjugate base, and then you can connect them like so. Base will make, as you can like guess already, right? Educatedly, conjugate acid, and then that's it, right? So that's your pairs, right? So of the like the conjugate pairs, right? So acid conjugate base, base conjugate acid. So now examples, right? So let's take a look at some examples, right? So well, here we go. It's a good example, right? So carboxylic acid, quite literally an acid, right? Reacts with the base, so maybe it's going to be some kind of like secondary amine, let's say, right? So like this, and that, or maybe let's make it tertiary, right? So because why not? So that's going to be triethylamine with a lone pair. Lone pairs on oxygen can be also shown. So we are going to break this OH bond, and then we are going to make our conjugate base and conjugate acid. Let's see what happens, right? So base loses an H, so this, or the proton rather, so the proton will be lost by the acid. And then as a result, you are going to make your thing, right, which is going to be that. So that's your acid. Now this is your conjugate base. So that's your pair, right? So now the base, the amine, right? So we'll be looking like this. So that's the basic amine. So this will have to act as a base. So what do they do from the general chem perspective? They accept H plus, right? So then we're going to add H plus to the amine, not to like any random atom in the amine, but specifically to this kind of like lone pair that will be able to make the single bond, right? So then you have here N, that's your ethyl, a little bit crooked, but shoot. And okay, good. So then I finally make an H bond, and then I know that nitrogen lost one electron to make this bond happen. So we're going to give it a positive charge. That's it. No lone pairs left over, right, on the nitrogen atom at this point. So, and then base makes what? The conjugate acid, right? So if you just practice, like do some self-practice, for example, like take some sort of like acids, right? Maybe like think about the name, octanoic acid, what is that, right? So draw that structure and then draw some kind of like secondary amine, primary amine, and tertiary amine, right? Just any examples of those amines. That's not too much to ask. So I'm just kind of like thinking about the classification of amines, right? So that's kind of like as basic, pun intended, as you go when you think about amine bases. So, and then how do those interact with the carboxylic acid of some sort? And you will see there's going to be the same pattern, right? No matter what kind of like thing you have, right? So in terms of the acid or the amine. So acid will always kind of break the OH bond and make the like counter ion, anion of the acid, right? And then the H plus. H plus will always go to the amine base, right? And then always the NH bond will be made. Of course, like those like things will be like whatever there is all else attached to the amine, it will not be kind of like touched. Those three ethyls stay three ethyls, right? Maybe it's going to be three phenyls, they will stay three phenyls. No worries here. So, and then you are going to make the NH bond, and then always the N will become positive, right? So you can just kind of like do that with any combination, and then you will kind of like have practice with that, right? And then you will also call them who is acid base, right? Where they are, and then who is conjugate base and conjugate acid. Notice acid base are by convention. On the left side, these are the reactants, right? In our case, in other words, and then the conjugate things, the conjugate compounds are going to be on the right side or on the product side. All right, so then what else? Nomenclature. So that's a big topic. So, but this is going to be kind of like present on the exam as well. So just look at your nomenclature things, right? So that's up to you to review. We cannot physically fit here anything in terms of that. So only some kind of like common things I would say, right? Because what I saw or heard from the individual meetings, that people were like, okay, well, I'm like overwhelmed by the nomenclature, right? So, and then this is like a very general question to which I can give like a general piece of advice, I guess, right? So when you look at some kind of complicated compound, right? So maybe it's going to be something like that. So it will for sure have the famous benzene ring, right? So, but it's not going to be like that simple, right? So if it would be great if it were just benzene, but oftentimes it's not, right? So maybe it's going to be like this. Okay, so we have this guy, right? So this is going to be called what? Aniline, right? So you look at this compound, it's going to be substituted benzene. Then maybe it's going to be even more substituted like this, right? So you have something like that. And then maybe you have this guy, right? So now like people become overwhelmed sometimes, right, by this structure. But here, just kind of like think about that, right? So how you can break it down into the bite-sized pieces, right? So like common motivational advice. So here we go. So what do I see, right? So as like one of my instructors was saying, like, tell me what do you see? So maybe you can see that, right? So why is that? So because that was happening, this like thing in the circle was present like honestly from the beginning of the semester, right? So like if you pay close attention to the details, it's a lot, so I know, so but still you will be able to recognize this as a nitro group, right? So this is something familiar. So what is that, for example, here? So like that piece, right? I'm not talking about like the combination of this like chain with the ring somehow, right? We never had that kind of, it's like a very specific piece, right? Very complicated. Compared with just this chain, this is less complicated, right? It's just the alkane chain, specifically made of 5 carbons in a row. And then what's that? That's going to be our pentyl, right? So for example, this is our pentyl group. This is a nitro group here, not amine, not nitrogen with oxygen, right? So nitro group. So that's just going to be the convention. And then if you look at this piece, yeah, you can like break it down into benzene with amine, but also it's going to be a good idea to notice that kind of like you have this specific name for the combination. When you have the benzene ring with amino group attached to that, it's going to be aniline, right? So this is aniline. So, and then we oftentimes use the name of aniline in naming substituted anilines, right? So that's kind of like what we have here. We can call it like aminobenzene, right? So, but it's used maybe in like 1% of the cases, honestly, although it could be legitimate, right? So the more like conventional way and accepted kind of like throughout chemical sciences is to call this combination aniline, not aminobenzene, right? So although it will like still sound right, but yeah, we're going to go with aniline, right? So we're going to recognize those kind of common, relatively complex building blocks, right? So that happen to be present in some organic molecules, right? And then in addition to aniline, you didn't have like, let's say 77 compounds, right? So that have some kind of specific combination of the benzene ring and some like random function groups, right? So you had a like pretty limited number of those common name organic compounds, right? That was aniline, toluene, benzoic acid, and I think that's it, right? So aniline, toluene, benzoic acid, phenol. So it was four of those, right? So now you hear those words, it's going to be a good idea maybe to pause, right? And then draw them for yourself or review them. So because those would be like very useful to know, right? So now here we go, right? So like, how do you name it? Now we need to number the carbons, right? That's one of the approaches here. So aniline will have carbon number 1, the one which bears the NH2 group, right? So now we're going to go either clockwise or counterclockwise, and then here we go. So if we go this way, we're going to go to be like this: 1, 2, 3, 4, 5, right? So pretty high numbers, right? So if we go this way, clockwise, then we're going to go 1, 2, 3, 4. 3, 4 is lower, right, in terms of kind of like the numbers. Together than the combination of numbers 4 and 5. So 3, 4 combination is lower than the combination of 4, 5, right? So just by comparing the numbers. Okay, so then consequently, we're going to name or number this cycle clockwise: 1, 2, 3, 4, right? Instead of counterclockwise, which will give you the higher combination of numbers. So here we go. So on carbon number 3, we have pentyl. On carbon number 4, we have nitro group, right? So those things need to be arranged now alphabetically, right? So and then here we go. Let's start stringing them, right? So we have N, M, and O, P, right? So N comes first in the alphabet, then it's going to be P, right? So nitro, pentyl. Nitropentyl, and then it's going to be kept by the name of the compound, which was substituted with those two substituents in like circles, right? It's going to be aniline. Aniline is going to be the name of the kind of like the base name of our compound here. Pentyl aniline of some sort, right? So now we need to say to which carbons those guys are attached. Carbon 4 bears the nitro group, 4 nitro, right? So carbon 3 bears the pentyl group. Even though 4 is higher than 3, right? So they need to be going like this, not like 3, 4, and so on, right? So, but they happen to be a 4 and then 3 because of the alphabet sequencing of the names of the substituents, right? Which takes precedence over the sequencing of the numbers in the name. So that's it. So we have 4 nitro, so 3 pentyl aniline. So that's your compound. And name exemplified, right? So then what else? So like common thing again, so that will be kind of like happening again and again, right? Pretty much kind of like almost 3 points at this point, right? So that's the functional groups, right? So that according to this diagram of knowledge is going to be our factual knowledge, so to speak, right? So you just know them functional groups, and then what they look like, right? So what do I mean by that? So for example, if you have the group like this, right? RSH, right? So that's what it looks like, right? So this is going to be our functional group here, like it could be circled, right? And then the question is like, what's the name, right? So just write the name of this, right? So it's not like sulfuric acid, for example, because sulfuric acid, for example, right? So looks like this, right? And then even though they have some similarities, they look completely different, right? So this is like H2SO4. This group here doesn't have any oxygens, right? So that's like what we think about when we want to distinguish them, just kind of like specific details, which are kind of like constant, right? So like as you go through chemistry, so the functional group of thiol will remain to be SH, right? Not like SH2 or SN or SO somehow, right? So it's going to be like functional group of the nitro group will be NO2, not NH2. NH2 is amine, right? So if anything, so it's not a nitro group. So because they are different, right? So even though they have some similar elements such as nitrogen, so but you also need to be able to see what the difference is in terms of the atomic composition, right? So also the specific attachment, right? So if you think about maybe like carboxylic acid functional group, right? It's going to be looking like this. So that's your combination, right? So that's going to be some kind of like R here, whatever. Let's just imagine it is a pentyl, right? So for the fun of things. So now you have this. So this is going to be your carboxylic acid versus this, guys. So let's say R, right? We have this, that one, and then maybe we have here this, right? So it's going to be some sort of cycle, right? So that's like cyclopentane or something like that, right? So pentagon here. So in this situation, this group will be the ester, right? So that's going to be your like ester group, especially if we take into account this carbon. Okay, great. So now we can say that's not carboxylic acid anymore because there is no OH bond as opposed to this one, right? So here you have the OH bond. So that's going to be your carboxylic acid, like peculiar element, right? So ester almost looks like carboxylic acid, except there is no OH bond in the carboxylic acid. So if you see the structure like this, you cannot call this the carboxylic acid group, right? So it's going to be an ester. So, and we didn't have any other cases when you have some kind of else attached to the oxygen here. It's going to be only either H or carbon of some sort. If there is a carbon, right? So typically in our case, it's just kind of going to be some sort of alkyl chain or cycloalkyl chain, right? Or maybe phenyl ring. So nevertheless, they all have carbons attached to like oxygen. In this setup, then you're going to have the like ester, right? So ester, not ether. Ether is different. Words are similar again. So, but the ether is going to be a different one. That's another common mistake that people were making, right? So if you look at the ether, it's going to be like this, right? So maybe you have some kind of like COC combination, right, of atoms. And of course, there's going to be some kind of like other atoms, maybe like hydrogen, and then maybe you have another hydrogen, and here you have maybe something like this, right? Let's just be a little bit more diverse. So that's going to be your like ether, right? So whatever I kind of like highlight with this oval or bean-shaped thing, so it's going to be our ether functional group. So just kind of like be aware, it's going to be about the skill of like paying attention to details a lot. All right, so then some kind of like reactions, right? Let's take a look at reactions now. So in terms of reactions, so what can I say, right? So these are all like reaction types that we have seen like throughout our journey in this course will be good, right? So you have, for example, let's take a look at item 6, right? It's going to be our reactions, right? So here you go. Like very common reactions, which you can see a lot, it's going to be like esterification, like ester formation, right? So ester formation. So esterification. So this is going to be good, right? So to review, so typically what happens is that when you have an ester of some sort, and we have reviewed it just a week ago, I guess. So you need to have the carboxylic acid, which will react with some sort of alcohol, right? So which is going to be like this. So what happens in this course, right? So according to the mechanism, which is going to be the like advanced chemistry term, right? So, but we can just throw it there as a word, and that leads to the result, right? So what happens according to the mechanism is that this one will be eliminated and this one will be eliminated. If you look at the circles, then they will be combined, right, into the side product, and then there's going to be nothing more than HOH or water, right? So consequently, you have to have the connection between this carbon here and this oxygen over here, so which will lead you to the formation of the ester. So I'm just going to show the general structure using some kind of like general structures of the acids, right? So those groups will stay where they used to be, R and R prime. Don't kind of switch them randomly, right? So I think people have been pretty disciplined in exam 4 about that, but just kind of like warning, right, to keep doing a good job. So, and then here you go, right? So that is your ester thing, right? So esters can undergo hydrolysis. Basically, it's going to be the backward reaction, in which case you are going to reobtain or obtain, right, your acid and the constituent alcohol, right? So they used to be in a part of the ester. So it could be reversible, right? So if we take this ester, right, and apply the like acid, for example, hydrolysis, then we'll be able to receive back the respective acid and the respective alcohol by breaking this bond, right? And basically what you see on the left side of this bond, just make it into the acid, right? All you miss here is the attachment of the OH to this carbonyl carbon. Once you do that, once you attach OH, you make your acid back, right? So here, all you miss is the H attached to the oxygen. And once you do that, you will regain your alcohol upon the hydrolysis of this guy. Right. So yeah, hydrolysis types could be like acid and base. So many people are like noticing that, okay, well, you cannot quite say true or false about the question that ester hydrolysis requires the presence of the base. It could require also the presence of the acid, and then we'll still have the hydrolysis, right? So just like think about that, but now it's up to you to review, right? So again, just some common examples of how we do the hydrolysis, right? So like think about what else like could be like fair game. So we will have of course, the good old proton transfer, right? So like you have some kind of carboxylic acid reacting with the water, right? So that is not hydrolysis because this is not an ester, right? So, and then this is going to be just a proton transfer, right? Acid reacts as an acid, and then it will make your counter ion, right? So it will make the anion, which is going to be also known as a conjugate base, by the way. And it will be looking like this, right? Maybe throw in some lone pairs, specific number, right? Of course. So, and show your conjugate acid. Water is amphiprotic, which means it can act as a base or as an acid, depending on the circumstances. So here it acts as a base. Water is a base in these circumstances. It will form the so-called H3O plus or hydronium ion, which will here be known as or labeled as typified as conjugate acid. So this thing can technically donate H plus sometime down the line, right? So then what else? So think about the thiol reactions. How do they react, especially with heavy metals? Divalent heavy metal anion, right? So that's going to be another good thing to think about. So we took a look at the oxidation already. So then ether formation. How do ethers form, right? So they can be formed in various ways. So, but typically it could be, for example, two identical alcoholic molecules or two different alcoholic molecules. They can form an ether, right, under certain circumstances. So, and it's going to be like this. So we have the H2SO4 as a catalyst here, right, at 140 specific temperature. And then we're going to basically eliminate H from one and OH from another. So guess what? It is water that will be the side product. And then you're going to make the connection like so between those two big dots, right? So and now it's going to be just kind of like error proof. Basically, all I need to do is just redraw them and connect the dots, right? And don't and not lose the parts. So that's it. That's your ether, right? So that you form here. Also think about halogenation reactions, right? So that was about alkene chemistry. So, or alkyne chemistry as well. So if we let's show some sort of alkyne, right? Because why not? So I'm going to show the, what's it called? Darn. Line skeletal drawing of the alkyne. It's going to be like that, right? So some kind of R group. Let's say it's going to be R. Let's say R is a phenyl, right? So just think about it, what it sounds like, right? So, and then here, what I need to think about is that we'll have the phenyl, right? So it's going to be like the electron from the phenyl. It will lead to the bond connected to the triple bonded carbon. And then here we have on the end of this bond another triple bonded carbon, right? So then we can translate it into this, right? Um, so all we miss here is an H, right? So this carbon has no H's. This carbon has one H, right? Three bonds, fourth bond. Three bonds, fourth bond. That's it. And then R is a phenyl, for example. So, well, maybe let's just draw that, right? For the practice of alkene structural drawings. So you will have this here. So that's your like alkyne, right? So it can undergo the, for example, halogenation processes, right? So let's just add one molecule of bromine to that and see what happens. So one molecule will break only one of those bonds, right? One pi bond will be broken. And then you can sense that we are going to connect the dots quite literally, right? To form the final product, which will be like this. So we'll have this phenyl ring, which will stay intact, right? So that's like a trap to some extent. And C, double bond will stay, not a triple bond anymore. CH, right? And you're going to add a couple bromines, right? To that combination of carbons. Br, Br. So of course you have to break this like Br bond, right? So otherwise the reaction is not gonna go. So now you have CBr, CBr bonds. So these are your new bonds. Double check yourself, right? So you have four bonds, you have four bonds here. So all good, right? So for the carbons, right? So now think about your potential review questions, right? So what are the hybridizations here on these carbons versus these ones, right? What are geometries? So things like that. So yeah. Yeah, so that's like what we have in terms of the halogenation, right? So we can add more halogen atoms. So let's say we're going to add two Br molecules, right? So now we're going to break the second pi bond, right? And in this case, it's going to be no more second pi bond here. So only sigma bond will stay. And then you're going to have, again, a different hybridization pattern. It's not sp2 anymore, it is sp3 because you have what? Four single bonds, right? So think about geometry, the like pattern of bonding around sp3 carbons, things like that, right? So, and then still all carbons here are tetravalent, right? So we're in a good shape. So yeah, then of course, so we reviewed that like multiple times, but it's now for you to review, right? Think about the condensation reaction that happened between aldehydes and alcohol, or ketones and alcohol, right? So that is just from the like terms perspective, it's going to be aldol, not aldol, but acetal formation and ketal formation, right? So typically when we think about those words, we go from hemiacetal to the acetal. We go from hemiketal to the ketal, right? So like think about those things and how they work, right? So for now, let's maybe take a look at some example, right? So let's start with a ketone of some sort, right? So some kind of like random ketone, which will be looking like this. And now it will, let's just show the full situation, right? When and it's going to be similar to aldehyde, by the way, when it reacts with consecutively two molecules of alcohol. Sometimes it's going to be, okay, well, you have a ketone and you add one molecule of alcohol, then you add the second molecule of alcohol, right? the outcome will be you will form the ketal at the end of the reaction, right? Sometimes it could be like you have one molecule of alcohol plus two molecules of alcohol, right? Oh, sorry, one molecule of ketone plus two molecules of some random alcohol, right? So then here you need to understand, okay, well, total two molecules of alcohol will have to react. What are we going to make? We're going to make a ketal at the end, nevertheless, right? So it's going to be a good idea to show it in step-by-step fashion, right? So here you go. So you will have some kind of like alcohol. Let's make it like that, right? So, and then it's up to you to decide what those R groups are. So just make them maybe phenol, isopropyl, and isopropyl, right? Because why not? So yeah, these are your examples. And now here, what you need to care about is just the general scheme, right? So you'll need to form the OH bond and need to form the CO bond. Let's see what happens, right? So this is going to be our reversible process. It is assisted by an acid. And now we're going to make our stuff, right? So we're going to show the carbon here. Those stay intact. So OH bond, so then you need to sacrifice one of those bonds, right? Excuse me. To keep the oxygen divalent. Okay, check. So now carbon-oxygen bond will be formed. And here you see, right, carbon becomes tetravalent. So it stays, tetravalent. Here used to be tetravalent, tetravalent as well. Because you broke this bond, you didn't keep it pentavalent. You did a good job, I hope. So this H is gone. This oxygen used to be this oxygen. Now it's here. Divalent, divalent, right? So we broke that bond. So H is gone to make this bond top, right? So now you have your so-called hemi-ketal. I'll just say it verbally. So now you can add the second molecule of the same alcohol. That's going to be your next step. Same. Sameness is indicated by this like R double prime. The OH bond will be broken. And now here we eliminate OH and H, right? And guess what? You are going to lose water. Proton is the sign of the acid environment. What are we making? So it's even going to be even easier. So you're just going to be connecting this dot with that dot. And then this is going to be your stuff. Or, strictly speaking, ketal, full ketal. Or okay, that's double prime right here. Double prime. So this is your ketal that you have just formed. In terms of the hemiacetal and acetal, literally all that happens is going to be shown in color. Let's do the like red. So let's imagine that there is an H, right? So that's going to be your aldehyde. It's going to be here, and it's going to be here. So that's your route, abbreviated severely, from, in terms of my drawings, from the aldehyde to hemiacetal to acetal, right? So if there is no R, triple command Z, shoot. Okay. If there is no H, if there is a R, maybe R stands for, let's say, methyl and methyl, right? Or it could be like butyl and butyl, right? That's the point, right? So there's going to be carbon, not an H. Then it's going to be kind of like this R stays here and there. And that's going to be your hemi-ketal and ketal. All right, so this is, I think, good. So one more kind of like thing to think about, right? So we're talking about a lot of the acid-base properties and proton transfer. Now let's talk about some balancing, right? So something to balance. We did it literally on the board. It was done by one of your peers, right? So it's like very like common question that we were doing in class. And it was part of like worksheets, and it's honestly part of the Gen Chem knowledge, right? And your knowledge, your ability to balance reactions which go beyond to like one-to-one reagents, right? So what do I mean by this? It's when we have 1 to 2, right? Ratio. Basically, how does it happen? It could happen, for example, when you have one molecule, let's say an alcohol of some sort, right? Alcohol, by the way, it was one of those like true-false questions, right? So they could be acting as acids because they have this polar OH bond that can break, and then you will guess what? If that acts as an acid, and you break this OH bond, right? So even though it's not a carboxylic acid, you should not be shocked, right? You need to be able to think and say, okay, well, if it's an acid, it has to form the H plus, right? And indeed, H plus will be formed. So, and then this is going to be your counter ion, RO minus, right? So that's how alcohols will dissociate, right? So let's just make this like insert, so to speak, right? Or inset, whatever that is, right? So that's your alcohol dissociation. However, we can take this a little bit further, and then basically we can show the acid-base reaction, right, between an alcohol and some sort of base, right? Let's make it, for example, um, magnesium, right? I think that's what we did once in the past. Magnesium hydroxide. So here you see, so there are two OH groups or two hydroxide which are present in the molecule of magnesium hydroxide, right? So one molecule of the alcohol can donate one H plus. To balance it, right? So you are going to have to use two molecules of the alcohol. Why? Because look at this. Now you have two H pluses and two OH minuses. What does it make? It makes two HOH, or it makes two molecules of water, right? So if you don't balance it, right, you will have one H plus upon the dissociation, right, and the exchange of the ions, and two OH minuses. Then you will end up having HOH, and OH minus will just chill, right? So that's not going to be good. So because we need to balance the reaction, to that way like minimize the charge, right, that will be generated. So yeah, you cannot just like leave like charged species randomly, right? So they will have to be balanced, and then yeah, that's what we will achieve by putting down ourselves the stoichiometric coefficient of 2 in front of the alcoholic molecule, and just you can put it in parentheses, signifying that you will have two molecules of this alcohol, right? So now you're going to be kind of like very close to your proper answer, right? So you're going to have magnesium, which has a charge of 2 plus, by the way. And then if you break this OH bond, you are going to generate RO minus, but you have two molecules of alcohol. So you're going to generate RO minus twice. And now you have the proper salt, right? So which is going to be magnesium 2 plus, and then you have two anions of this kind, right? Let's think about this in terms of magnesium. Let's say magnesium is 2 plus, and then your anion, some kind of anion, let's say chloride is minus, right? So you cannot leave it like that, right? So it's not going to work, right? So you need to be able to put the coefficient of 2, and then you'll make the proper formula, right? So it's going to be kind of like balancing inside the formula. It's like from your Gen Chem knowledge. Now you have charge of 2 plus, 2 multiplied by minus 1 becomes 2 minus. Total charge is 0. Here is the same thing. You have charge of minus 1 on the RO minus anion multiplied by 2 becomes minus 2. And 2 plus on the magnesium, right? So then you are going to have a total charge of 0 on this compound. Total charge of 0, all good, right? So now you are going to deal with your waters. You have two OH minus and two H pluses, right? So consequently, it's gonna be like this: two HOH molecules will be formed, or two molecules of water will be formed. You can leave it like that: two HOH or two H2O. So just think about it, and maybe kind of like do some examples, right? With this, also you can take it up a little bit further and get rid of this like magnesium stuff, right? So, but switch it to, for example, aluminum, right? So let's just imagine aluminum, right? So we have aluminum hydroxide, or what else is trivalent? Maybe something else. Okay, let's see, aluminum. Maybe even like make it like thallium, right? So I think thallium can exist as thallium 3 plus, right? What happens here, right? So now it's going to be up to you to balance this reaction, right? So products will be the same, right? So you'll still have this kind of like breakage, right? So you'll still have the salt instead of magnesium. Thallium 3 plus will be combined now with RO minus, right? So thallium 3 plus. But now, what's going to be here, right? So that's going to be like up to you to decide. Now, what's going to be the coefficient here, this kind of like subscript, right? So, and now what's going to be the stoichiometric coefficient here? How many water molecules are you going to make? So I'll just leave it as a cliffhanger for you to think about, but honestly, that's your Gen Chem knowledge, and it's all about balancing the equation at this point, and you have even the products, right? So now, and there's going to be the bonus point question, but it's going to be kind of a non-scientific thing. It's just going to be like your opinion, so to speak, and we will be good. So yeah, at this point, I thank you for your attention, and we are done. Bye, everyone.